produces a magnetic field that's in the vertical direction of some Teslas, which is, I mean, these are also very strong magnets. They're much stronger than all the magnets you see in like NMR at your doctors. Okay, this was supposed to run last year already, but then after 9 days, this happened. So there was a fault in the electrical connection between two of the magnets. So I mean, the electricity is flowing in superconducting wire through all the magnets, and then at some point the conduction was bad and it heated up. So it heated up 100 magnets, quenched, went 100 degrees up in temperature, and 53 were terminally damaged. I mean, here you see the point where it happened. So I mean, these two things are supposed to be parallel, right? And 6 tons of liquid helium were lost, so the whole tunnel froze instantly at that point. So it took them 14 months to recover, but luckily now, since November again, they're running. Okay, so what do we want to do? I said we want to find this missing particle called the Higgs. We also want to find, there's a theory that all particles that I've shown you on the previous slide have further so-called supersymmetric friends, which are needed for very good theoretical reasons, but haven't been seen so far. But we hope to see them at LHC. And then there are more things. So I didn't put question marks here because I'm pretty much convinced that we will see them once the thing is actually working. And then maybe we see dark matter, which is stuff that we know from cosmology should exist. Maybe we see extra dimensions. Maybe we see mini black holes. And of course, we hope for surprises. I mean, we're doing research. We don't know what we're going to see, right?
Dragons.
Dragons. Yeah, I want to have a picture. But there's one thing. Will it destroy the Earth? Especially because of black holes. There's a quick answer: no. And if you want to know why this no, I can come back to this in a Q&A. Okay, this is the pit of the experiment of the, I think this is CMS. So here you see the hole where they bring stuff down. This is there a person somewhere on this picture? No, but I mean, this is one story. You see bottom right. Ah, here's the guy. So you see how big this thing is. So in this pit, they fill with one of the detectors. So how does the detector look? I mean, this one at the surface, the beam pipe goes here. It's taken apart. I mean, this picture was taken when it was constructed. This one, CMS, was constructed on the surface and then lowered into the pit. The other detector, Atlas, was built underground. Here's again a person. So before I explain a bit more how the detector works, I should say, let's look again at the proton. This was the red thing, and I claimed it consisted of 3 quarks. And I was lying when I said that, because actually, when you look at it closer, you see that there are many quantum vacuum fluctuations, and there are about 2,000 particles popping in and out of the vacuum, making up, I mean, these spring lines are also particles that go from here to here, and there are more quarks. They're all in there. It's just the kind of 3 outermost ones that I displayed in the first picture, but we're really colliding things that are made up of 2,000 smaller things. And then we collide them and look at the debris, and this is pretty much like we're colliding grand pianos. I mean, at high energies, we throw 2 pianos together, stuff flies out, and then we try to determine how a piano works. From the debris. But the amazing thing is, people can do this. So this is a simulation of how such a collision looks like. So there are all kinds of, I mean, stuff coming in from here, stuff coming in here, and stuff flying out, and you see it curls up because you put a very strong magnetic field inside these detectors. So anything that is charged goes on a curved path, and from the curve you can determine the momentum, or if you like, the velocity of the particle. There are some uncharged things that fly out directly. So this is a simulation from one of the detectors. So this is the other detector. actually, I'm going to switch now. Oh, that works. To this little flash animation. So this is the same detector, and now CERN has great. This at CERN's great PR website. You can download thousands of pictures and these stuff as well. So as I said, there's the beam pipe. I said, okay, no beam pipe. Let's do first the tracking detector. So the most inner part of the detector. This is where the collision happens. In this part of the detector, this is filled with silicon. This is basically filled with like the CCD elements of a digital camera, just fill the whole volume. And because then from exactly through which pixel the debris flies, you can determine the track of the particle. So let's try the beam pipe again. Maybe. Yes, there's the beam. So the beam pipe goes here, and now you have two particles colliding, and boom, they go. And different particles that you produce in the collision make it through different parts of your detector. So we've already seen the tracking detector where everything goes through and you record the tracks. Then there's the so-called hadron colorimeter. So anything that's made out of quarks is detected in that part. Let's click on this. So it's this. So basically, this is steel interspersed with, how do you say plexiglass in English? Plexiglass. Acrylic material where tiny flashes of light appear when a particle goes through. So, and these particles get stuck in the plexiglass and also in the steel, and you see how much energy is deposited in the detector from the flashes you see in the plexiglass. And you measure the energy of these particles. Then there's a similar thing for the electrons. They get stuck at this part and get recorded. And then, but most of the structure, here you see, this is just, again, a huge superconducting magnet, because there's only one species of particles which makes it out to this part, which are the muons, remember these were the heavier cousins of the electron. They go through the inner parts of the detector, and they feel this big magnetic field, and then they're detected in these outermost parts. So these two things and the stuff on the outside. And then you can detect where they come up and try to reconstruct the two pianos from all the data you collect. So what do I mean when I should go to the other slide again. Ta-da. Atlas. So we've seen this. Okay, so now for you computer geeks. So the problem is, remember, there's one collision every 25 nanoseconds. So 25 nanoseconds, short time, right? They occur at 40 megahertz. And roughly there are 17 events in each collision, so you have an event rate of a gigahertz. And you have to bring this down to store away. Of course, you only want to store the interesting data. And it turns out most of the collisions are boring because you completely understand them. We're looking for the new stuff. And we only want to store the new stuff. And we expect 1 in 10 to the 7 are interesting. So we want to store 100 events per second. And this is here these are all tape drives, right? There's a robot that goes through to put the tape drives into the recording device. So, the big problem is, remember 25 nanoseconds, light traveled 7.5 meters in this time. And remember how big the detector was. So there's already the next collision in the detector long before just light had the chance to travel through the whole of the detector, and all these particles are effectively flying with the speed of light. So at any time, there are always several, the debris of several collisions in the detector just flying out like through the shells of an onion. And and when you do the data processing, you also have to process this data once every 25 nanoseconds, and you want to decide which to keep. So, if